if we are going to make a table to find intervals of concavity, and from that table find the points of inflections. So, if we're going to find concavity, you have to understand concavity deals with the second derivative. And then from there, once you have those second derivatives, you can find your concavity. When you see where concavity changes, then you have your points of inflection. So in order to do this, we need to take a second derivative. And when we look at this function, if you start taking the second derivative of that as is, you're going to have a nightmare on your hands with product rules. You want to simplify this before you start. It's always important to do that. So I'm going to distribute that x squared through to change this to g of x equals x to the fourth plus 2x cubed minus 12x squared. So that right there is g now. Now can we take the first and second derivatives? Mm-hmm. Yeah. The first derivative is just a tool to get to the second in this particular problem. So we take the first derivative. This is a really easy one to do, so we're really happy, hopefully. So this would become 4x cubed plus 6x squared. So, and then we have, this would be negative 12 becomes negative 24x. So let's now take the second derivative. That would be 12x squared plus 12x minus 24. So we now have our second derivative. Now, how does that help? Where do we go from here? Well, the second derivative, well, to find out where you might change concavity, which is your point of inflection, what you do is you set your second derivative equal to 0 or undefined. Now, would this ever be undefined? No. So we don't have to worry about that. But it will have it equal to 0 several spots. Now, those numbers are kind of big. I want to watch what I'm going to do here. Could I set this derivative equal to 0, right? But what GC have to all go into all those? 12. So can I pull out a 12?
Yeah.
That really makes it quite a bit cleaner. And that 12, can I ignore that 12 when I set and factor it and find the zeros of this second derivative? Do you notice this is kind of like a critical number? This process is almost identical to critical numbers. We're going to factor, negative 2 on top, 1 on bottom. What would that be? Is that 2 and negative 1?
Or negative 2 and 1.
Okay. Did I mess up? 2 and negative 1 be x plus 2, x minus 1. And then so when we set each equal to 0, we get your possible points of inflections are going to be negative 2 and 1. Now those are our possible points of inflections. Those are possible P of I. Points of inflections are, I call them P of I to shorten it up. But they're possible. We don't know for sure if that's the case. So the question is, we're going to make a table for intervals of concavity. So these two spots are possible spots where it might change. So those are our breakpoints on our table. So I'm going to make a table. And I have 2 breakpoints. Okay. My first breakpoint is going to be at negative 2. My second one's at 1. All right. So we make an interval for the first one would be, well, values less than negative 2. You can use the other notation as well. Next one will be from negative 2 to 1. And then you have bigger than 1. Those are intervals we're looking at due to our breakpoints of possible points of inflections. And then aren't we going to plug in values to the second derivative for each interval? So what we're going to do here is we're going to take the second derivative, make sure you put the 2 derivative mark, and put a number in negative that's less than negative 2. So would negative 3 be a good idea?
Yes.
Okay, yeah. And we're going to see if that's positive or negative. All right, I'll come back to that, but let's plug each one in. I'll write it for each one, then we'll come back and plug it in and find the value. So what's a good number between negative 2 and 1? 0. You're always looking for, if you can use 0, be very happy. It's like, yeah, I'm going to use 0. All right, and the last one, you're plugging the second derivative. Would 2 be good?
Yeah.
Could be anything you want. We'll go with those numbers. So now we plug them in, do some crunching, and we're plugging it into the second derivative, so be very careful. Now, does it matter if I do this one, or this one? Do you understand this one in red is actually probably easier to plug into? If all we're looking for is positives and negatives, I'm going to use this one. Now, could I ignore the 12 even? If all we're looking for is positive and negatives, can I just ignore the 12? Because that's not going to change its positive and negative value. So aren't I really just looking at these two? Think of that. So what I'm really doing is just going, okay, what's negative 3 plus 2 and negative 3 minus 1? Well, isn't it going to be a negative times a negative? And what's a negative times a negative? A positive. So guess what that means? It's smiling at you. Smile, which is called concave up. On that interval, we're concave up. Let's go to the next one. We're going to do the value 0. So that'd be 0 plus 2 times 0 minus 1. Won't that be a positive times a negative? Won't that be a negative? And don't negatives mean I'm frowning or sad? Sad little guy. So he's concave down. Last one, we're going to plug in 2. So 2 plus 2 times 2 minus 1. Doesn't it look like a positive times a positive, which is positive? He's happy again. He changed his mood. So he's concave up. So we now, have we finished a table, intervals, concavity? Do we have our table, and do we have intervals and the concavity labeled? Yeah, we did the first part of it. Second part is, where are the points of inflections? Well, the points of inflections are where it changes. Did we change concavity right here at negative 2? Did it change its mood? Yeah. Did it change at 1? Yeah. If it changed, it's a point of inflection. So now we've got to find the coordinate for the point of inflection. So the coordinate for the point of inflection, this is going to be negative 2 something, and it is a p of I, we just said it was. And the other one's going to be 1 comma something, and it will also be a p of I. How do we find the coordinate, the value that goes here and here? Be careful, you have to go back to the original. Now, could I use this one or the red? Would you rather fourth power or keep it to the lower powers? I think the top might be easier. Just depends on your number crunching abilities. It all depends. I'm going to use this one. So I'm going to do g of negative 2, which would be negative 2 squared times negative 2 squared plus 2 times negative 2 minus 12. What do we look like we get there? That would be 4 times 4 minus 12. That becomes 0. 4 times negative 12 is negative 48. It's a pretty low point of inflection. All right, next one is, let's plug in 1. What number? Plugging 1, right? To the original. So we got 1 squared times 1 squared plus 2 times 1 minus 12. So that's 1 times 1 plus, plus 2 minus 12. So that's 3. 3 minus 12 is negative 9. So times 1 is negative 9. So it's a negative 9 there. So right there are our points of inflections. Right here is our table of concave up and down. So each of our possible points of inflections were points of inflections. Not always will they be. Could we graph this? Could we graph these 2 points? Yeah. Could you then draw this little shape, these little shapes between the dots to get a quick sketch? Yeah, you know a pretty good look of this graph, meaning, don't you know if we quickly sketch this, watch what you'd get. The first value would be way down here, correct? The next value is going to be somewhere up there. And don't we know it goes up here? Are we okay with that? So somehow the graph we know has some sort of that look, maybe? Maybe? And then on the middle interval, isn't it kind of have that look? A frown for a little bit. And then on the other one, don't you have a happy again? Is that a possible look? I don't know exactly how it looks, but I know it has that look somehow. So I can kind of get a general look of what it looks like. Hopefully all this helps.